I'm going to do some examples on finding complex roots of polynomials. So we're told that z is equal to minus 4 plus 5i is a root of this polynomial, and we're asked to find the remaining roots. So it's a root of this polynomial means it's a solution of this equation, where that equals to 0. So the first step, I have one root, that's minus 4 plus 5i. So since this is a polynomial with real coefficients, so there's no complex numbers in front of the z's here, I have z cubed plus 11z squared plus 65z plus 123, so that 11, 65 and 123 are all real numbers. I know that any root of this equation will have its complex conjugate also be a root. So z is equal to minus 4 minus 5i is also a root. If minus 4 plus 5i is a root, then this must be a factor of that polynomial. Z minus 4 plus 5i. That must be a factor. And also z minus 4 minus 5i. So they must both be factors. Since, if I factorize that polynomial and I get those two factors, well then each of those equals to 0 corresponds to a solution. And I bring the thing in the brackets onto the right hand side and I get that root that I have above. So if those two are factors, I multiply them together to get one bigger factor, and then I'll figure out what the remaining factor must be, and hence what the remaining root must be. So let's write that down. Well, that's equal to z plus 4 minus 5i and z plus 4 plus 5i. So I'm going to get the product of those two things, and I'm going to use that then to figure out what the other factor is, and hence what the remaining root is. So when I multiply this out, I'm going to do it with brackets around here. So let's work that out. So I have z times z is z squared, plus I have z times 4 minus 5i, plus z times 4 plus 5i, times the two things in brackets multiplied together, plus 4 plus 5i times 4 minus 5i. So that's everything multiplied out. So that's equal to z squared. So you see the plus and minus 5 there, I there are going to cancel, and I'm just going to get z times 4 plus z times 4. That's going to be 8z. And on the right there, I have 4 plus 5i times 4 minus 5i. So in general, I'll write down the rule here. X squared minus y squared is equal to x plus y times x minus y. That's a general rule. So I can use that there to simplify that multiplication on the right hand side. It's just going to be 4 squared minus 5i to be squared. And of course the I squared is going to be minus 1, so that's going to turn out to be 4 squared plus 5 squared. So that's equal to z squared plus 8z plus 16 plus 25 is equal to z squared plus 8z plus 41. So that's a factor of my original polynomial. So that's a quadratic factor, it has a z squared. So the remaining factor can only have z to the power of 1. Any higher than that, and I'll get too high a power when I multiply it out. So now I can write down what my polynomial must be with that factor taken out. It's going to be that factor times some power of 1 term with z. So something like z plus a, I'll call it. Whatever's on the other factor it's going to be something like z plus a, because anything else won't work out. So I could say it's like az plus b or something like that, but I can see straight away that I can't have anything else in front of that z, or I won't get my z cubed in the original polynomial. So that's equal to my original polynomial. Here we go. Now what I need to do is multiply out that left hand side and collect up the terms for each power of z, and then compare them on the left and right. So that thing on the left there is equal to z cubed plus az squared plus 8z squared plus 8az plus 41z plus 41a. And if I collect up the like terms, I get z cubed plus z squared times a plus 8 plus z times 8a plus 41 plus 41a. So now I can compare that to my original polynomial. So I have z cubed and z cubed, which is fine at the beginning. So I know that a plus 8 must be equal to 11, because that's the z squared term. And I know that 8a plus 41 must be 65, and 41 times a must be 123. So that 41 times a should give it to me easily enough. If 41 times a is 123, that means that a must be equal to 3. And you can see that that works with the other one as well. A plus 8 equals 11. Well, that works for 3. 8 times a plus 41 must be equal to 65. That works too. So a equals 3 works. So now I can write down my, my factorized polynomial on the next page. So there it is with my a put in. Now I already have my two roots from that left side over here. And I just want the remaining root from the right side here. So z plus 3 equals 0 gives me a root, since z plus 3 is a factor. So z plus 3 is equal to 0, means that z equal to minus 3 is a root, and that's the remaining root. So if I write them all down, my roots are z is equal to minus 3, that's the real root. Z is equal to minus 4 plus 5i was given to me, and z equal to minus 4 minus 5i is the remaining root, and that's the 3. So I'll do another one. So another example, let's say I have this polynomial on top, and I'm told that z is equal to minus 1 minus 5i is a root, and find the remaining roots. So the first root, z is equal to minus 1 plus 5i, is also a root. So my two factors associated with those two roots are going to be z minus 1 minus 5i and z minus 1 plus 5i. So I'll just sort out those minuses and then I'll multiply it out. So that's z plus 1 plus 5i, and I'll keep that in brackets for the moment, and that's z plus 1 minus 5i. Now I'll multiply this out, so z times z is z squared, and I have z times 1 plus 5i, and I also have z times 1 minus 5i. And when I multiply the two things at the end together in brackets, it's 1 plus 5i times 1 minus 5i. So that's equal to z squared. The plus 5i and minus 5i cancel, and I end up with just 2z. And when I multiply that thing at the end, what I end up with is 1 squared plus 5 squared. So that's equal to z squared plus 2z. 1 squared is 1 and 5 squared is 25, so it's 26. So my original polynomial can be written as this times something else. So it can be written as z squared plus 2z plus 26 times some other factor equal to 0, the equation. So this other factor must have just a power of 1 on the z to make my z cubed in the original polynomial, and it'll be plus something. So I'll just put in a plus a here. We'll multiply that all out and then we'll compare the terms. So we multiply out, we get z cubed plus az squared plus 2z squared plus 2az plus 26z plus 26a. So I combine the like powers of z. I get z cubed plus z squared times a plus 2 plus z times 2a plus 26 plus 26a at the end. So now I can compare my terms. So 26a must be equal to 26. Also that means a must be equal to 1. And we can check my other ones here. 1 plus 2 here gives me my 3 which I need, and 2 plus 26 gives me my 28, so we're all good. So my final factorized polynomial, I have z squared plus 2z plus 26 times z plus 1. And of course I have already the two roots associated with this factor, and I just want the root associated with this z plus 1 factor. And of course if z plus 1 is a factor of this equation, if that's equal to 0, then my final root is going to be z is equal to minus 1. So my three roots eventually then are z is equal to minus 1 is the real root, and z is equal to minus 1, and then plus or minus 5i are my remaining complex roots. I'll do one more example. So here's another example. I'm given that polynomial equation on top. I'm told that z is equal to minus 5 plus I is a root, and find the other roots. So straight away I can say that z is equal to minus 5 minus I is a root, because it's a complex conjugate of the first root. So I have two roots, so the two factors associated with those roots would be z minus 5 plus I. That's one factor, and the other factor is z minus 5 minus I. And then I'll just sort that out a bit. Z plus 5 minus I, brackets, and z plus 5 plus I. So I'll multiply that out, and then I'll use it to find the remaining factor of that polynomial. So when I multiply it out, I get z squared. I get z times 5 minus I, and z times 5 plus I. And I also get 5 minus I times 5 plus I. I tidy that up, and I get z squared plus 10z. That thing on the right works out to be 5 squared plus 1 squared, which is 26. So that's one factor, or well, it's the product of two factors, but it's a factor. So my original polynomial can be written in this form. That's the factor I have there, and the other factor will have z to the power of 1, since overall it's z cubed, and we already have a quadratic term there on the left. I'll just put in some number a, and that, when I multiply it out, must give me back my original polynomial. So I'll multiply that out, and then I'll compare the terms. So multiplying it out, we get z cubed, that's z squared times z. Z squared times a is az squared. Then I'll do the 10z, 10z times n. Z is 10z squared. 10z times a is 10az. 26 times z, and 26 times a. Now gather up the terms. I have z cubed. I have z squared times a plus 10. I have z times 10a plus 26. and I have 26a at the end. So I'll start here at the end. 26a must be equal to minus 78. So that means that a is equal to minus 78 divided by 26 is equal to minus 3. And if I look at my other terms, I should find that minus 3 gives the right result in every case. So there I have 10 times minus 3 plus 26 is minus 4, and minus 3 plus 10 is 7. So that all works out. So a equals minus 3 works. So now I can write down my factorized polynomial. So there we had the quadratic factor with the two complex roots. And my other factor with the real root is going to be z minus 3. So if all that equals to 0, that was the equation I'm solving. So a solution for that is z minus 3 is equal to 0, and that means that z is equal to 3. So my three roots are z equal to 3, z equal to minus 5 plus I, and z equal to minus 5 minus I. And that's the answer. And that's how you solve for complex roots of a polynomial.